Thank you for joining us to talk about your paper that was released today. We'll start with the first question. What is the significance of your research on catalytic allylation of native hexoses and pentoses in water with indium? And please correct me if I butchered those pronunciations.
No, it's very good. Allylation,
Allylation.
right? So the significance of this particular work, as you focused on the ability to form a new carbon-carbon bond to a native sugar, such as glucose, or pentose, such as ribose, uh, is that making carbon-carbon bonds usually requires reagents and conditions that are not compatible with water. The majority of organic synthesis is done in organic solvents, and they're not water compatible because the protic environment destroys the reagent. So the challenge for us, and in fact, the challenge for much of carbohydrate chemistry when one wants to modify natural carbohydrates, are twofold. One is they're soluble only in water. And secondly, they're adorned with many hydroxyl groups, which, like water, are incompatible with most organic reagents that form carbon-carbon bonds. And what we were able to do is develop a reagent based on indium metal that adds a 3-carbon unit to the number 1 carbon of glucose that is an aldehyde. And that can undergo the addition of the 3-carbon unit, extending it from 6 to 9. Now, that had been done. We are standing on the shoulders of real giants who did that chemistry with tin reagents and also indium reagents in the 1990s. The difference is that they were using those reagents as stoichiometric reactants. What that means is for every mole of glucose, they needed a mole of tin or indium reagent in order to make a delivery. What we set ourselves the challenge to do was to use the metal as a catalyst. And by using it as a catalyst, we only needed a tiny amount of the indium to facilitate the bond formation, but then start all over again. So catalytic cycles run continuously, whereas stoichiometric reagents and reactants, one time and it's over. So the problem in modifying carbohydrates is they're twofold: water solubility and hydroxyl groups. Now, the water solubility, it turned out, it was known that indium reagents, organo-indium reagents that have a carbon-indium bond, are water compatible, and tin also. So that was known. The hydroxyl groups on native sugars are normally, when one does organic chemistry on carbohydrates, those hydroxyl groups need to be protected, which means there is another group that goes on top of it and prevents and removes the OH, so that it is now compatible with many chemical reactants. Carbohydrate chemistry is all about selective protection, so you can work on the carbohydrate where you want on the molecule. The fact that we're able to modify and modulate the native sugar in its environment of water and without protecting groups under catalytic conditions is the major advance, so that we only need a pinch of the indium to be able to carry out the bond formation. So why is that important? The process that uses tin and indium stoichiometrically then has a waste product. All that material you put in to affect the reaction, that doesn't go away, and you have to remove it to purify the desired product. And in the case of tin, that's a toxic metal. And especially if the end application of the chemical is in water bottles, plastic water bottles, or in syringes used in hospitals, or in food containers that are clarified from a plastic that I'll explain in a moment, then you have you really be sure that you remove every tiny, down to the ppm traces of that metal for its end use. So the reaction that we developed is to you take glucose and turn it into something that has a huge industrial impact in packaging.
That is fascinating. Thank you. So that's a great lead into the next question about the manufacturing implications of your research.
Okay, so let me take you back to around 2008 when I was contacted by a company in South Carolina called Milliken. I actually knew a couple of the scientists there from previous consulting with pharmaceutical companies, and one of them moved to South Carolina where he grew up and started working with Milliken. Now, I am known in the chemical community and from publishing hundreds of papers that I'm an expert in this process called allylation. And the allylation is adding a 3-carbon unit to molecules that can then be further elaborated. That's organic synthesis, making new carbon-carbon bonds to be able to make new molecules from feedstock molecules. And I've spent many years of my career learning how to do that. So they contacted me because of that expertise. And what I learned from that discussion was that a particular compound that they marketed was made from glucose by adding an allyl group to the number 1 carbon and then hydrogenating the unsaturated carbon-carbon bond that comes with the allyl. Now, the product that they sell is called Millad, Milliken Add, Millad NX 8000. What Millad NX 8000 is a polypropylene clarifying agent. So what that means is when polypropylene, which is a petroleum-based product from cracking, and it's produced on the 1 million metric tons a year worldwide. Because polypropylene is easily molded into any shape and form. So it can be made into car bumpers. It can be made into Tupperware. It can be made into bottles, plastic bottles. It can be made into hypodermic syringes. So polypropylene is an extremely versatile precursor to make all the products of modern life that we've come to enjoy. Now, of course, it is a fossil fuel derived material, and so recycling has to be an element of that. Now, Milliken does not make polypropylene products. What they do is they sell Millad 8000, NX 8000. Millad NX 8000 clarifies polypropylene. If you make a piece of Tupperware out of virgin polypropylene, it's translucent. You can't see through it. It's cloudy. But for car bumpers, for packaging that's colored, for things that you don't need to see through, it's fine. But there's a significant percentage of products that are clear, like water bottles, and like some packaging and hypodermics, and bags that we use all of the time and in hospitals for saline solutions and so on. Now, those materials are usually made from a different polymer. That's a polyphthalate. A phthalate is made not from polypropylene. It's made from a much more expensive building block. But when it's blow molded, it's clear. So what Millad does is it changes the crystal lattice form of polypropylene as it's molded, melted. Polypropylene, virgin polypropylene is just a white powder. But it's blow molded. It's heated to liquefy and then pressurized into a mold to make a product. And then it crystallizes, solidifies. What Millad does is it prevents it from becoming transparent, translucent, and it makes it transparent. So now you have polypropylene is the cheapest plastic precursor. So now you have a clear plastic. And of the 100 million metric tons of polypropylene that's produced every year, about 30 million of that goes into clarified polypropylene. And Milliken has 80% of that market. So they are really interested in a cheap way of making Millad NX 8000. So they contacted me because I'm an expert in allylation. And the challenge is, can you add that 3-carbon unit to glucose in water catalytically, because we don't want this horrible mess of tin at the end of the reaction that we have to purge and clean and show specs. That's expensive and wasteful. Now, there are 2 other chemical steps after that, which is a hydrogenation and a ketalization of 4 of the hydroxyl groups to make Millad. But those are really cheap. The big cost driver is making something called allylsorbitol. Allylsorbitol is exactly what happens when you add an allyl group to glucose. That's it. Those 2 things, and you get allylsorbitol, and that's all the skeleton of Millad NX 8000. Okay, I'm making this a long story. So they hired me back in 2008 for as a contractor to try to develop a catalytic process to do this, and they paid for a postdoctoral researcher. We spent a year. We came very close. We came up with a catalytic method to allylate sugars in water, but it only worked for 5-carbon sugars. It didn't work for glucose. Glucose is the hardest sugar to functionalize because, as many chemists will know, glucose exists in a ring form, and the carbon that we need to react is not available. It's only 0.1% in aqueous solution. So the chemistry has to be really robust to capture that and drain it over to the desired product. So we tried, we came close, but we couldn't allylate glucose. And so they're not a research company. They don't have a big research budget. And they said, sorry, we just can't fund it anymore. Now let's fast forward, which will come to another question coming later. In 2020, when I was involved in creating the MMLI AI/chemistry sponsored institute by the NSF, one of the 5 thrusts that we considered for AI-enabled something was manufacturing. And we were brainstorming in January of 2020 after the call came out for the first round of institute funding. And I remembered Millad NX 8000. And I said, maybe we can revisit this. It's been 12 years. I don't think that they've changed their process. They, in fact, hadn't. So let's make this a problem where we could leverage AI to solve a problem that has huge commercial implications. So we agreed. The team agreed on that. We wrote up as part of the proposal. We were funded in August of 2020 and started the first round of the institute. We're at the end. We're clubbing to the end of our first 5 years, and right now we're very busy with the renewal. Next week we have a site visit.
Oh, yes.
So we were in the first round of the first 4 AI institutes that the NSF funded. So we started. We got funded. I went out to hire a postdoc who would try to solve this problem and leverage artificial intelligence to solve it. So that is the manufacturing implication. I can tell you perhaps, well, the question 3 actually is new products, conveniences, services. So why don't I let you ask that one and I'll respond to it.
Okay. Well, thank you. It sounds like the manufacturing implications are massive. And it's so neat that it kind of came full circle. It sounds like you're kind of the catalyst for this to have come about. So yes, let's go to question 3. How could the average person or consumer be affected by your research findings in terms of new products, conveniences, or services?
Well, as I've already mentioned, Millad NX 8000, which is what this process will make, is already used in 30,000 metric tons a year for clarifying polypropylene. So what our process will do, and what I can say is that we have patented the process, And I waited until the patent was issued in order to go back to my friends at Millikan who were still employed and still in the additive business and tell them, hey, guess what? I've now finally got a catalytic process to make allyl sorbitol. And they were beyond excited about it because they are still practicing the old process with stoichiometric amounts of tin. And so I told them it's patented now. I'm free to discuss it with you. So let's talk about how might this be implemented. I gave them the preprint of the manuscript. We had lengthy discussions about what would be involved in the manufacturing, and they have now done what's called a techno-economic analysis to see how much money it would save them, but then also how much money it would cost to implement this new process and phase out the older one, which obviously they paid a lot of infrastructure to do. So to the average consumer, you're going to see more and more clarified polypropylene in your packaging materials, in the things you see in hospitals, in your Tupperware, in your clear plastic water bottles from this product. But the good thing about it for you is that it's going to be cheaper because the process will make it lower cost, but it's also for the environment, it's beneficial. Because what Millad does is it lowers the processing temperature. Normal polypropylene is blown at around 240 degrees Celsius. And by adding the additive to clarify it, it lowers the processing temperature to 190, which is about a 20% energy savings in having to heat the molds. It also improves the recyclability so that this plastic is more easily recyclable compared to the polypropylene that's not clarified, so that it will increase the amount of polypropylene that can be recycled, and it will also lower the temperature. So, an example is Millikan claims about 1,000 tons of Millad in an injection module. By using it, it saves about 3,600 hours of production, which is equivalent about $150,000. So there will be a cost saving and there will be an energy saving, which is better for the planet if we're going to use a fossil-derived material for these products.
It's a win all around. You touched upon the next question a little bit, but what brought about your research project in AI-enabled molecule manufacturing?
Well, that's a little bit of a funny story. It turns out that our discovery of this process that uses just a catalytic amount of indium was already in the literature, and it was published in 2008 by a group in Japan from Kobayashi's group, and he had reported the use of indium as a catalyst, indium metal, to add to ketones and other kinds of functional groups, but not to carbohydrates. But he also showed it was in water. It was already known indium was compatible with water. So we decided this really looks like a way, since it's water compatible, the indium is reusable, let's see if it works on glucose. And bingo, the first time we tried it, it worked beautifully. We had to do some optimization of the reaction, but then we showed it works for all of the hexoses. It works for amino sugars. It works for keto sugars. It works for pentoses like ribose and arabinose and xylose. And it works perfectly. There are no side products. There's only a single product. It's extremely clean. And we were already in possession of a solution to the problem before we needed AI. So we thought, this is great, but we didn't need any AI to find the answer. But what we also realized is that for manufacturing purposes, I could get into a little bit more of how the reaction works, just for the audience to appreciate how we got to the AI step. When you run these reactions, we use indium metal. it looks like just a piece of metal. It could be a piece of magnesium, a piece of iron. It's not iron is not shiny and white and silvery colored, but indium is. But it's very soft, and we just put it either a piece of this metal in the reaction solution or some powder, indium powder. And from the stirring during the reaction, the powder gets hammered into a piece of foil because it's malleable. At the end of the reaction, you see that all of the glucose is consumed, and then you can take a tweezer and pull out the indium. It's unchanged. It was unbelievable. And Kobayashi also had noticed this, but we thought, this is incredible. How is this happening? And we actually did 5 cycles where we put in 60 milligrams of indium. We took it out, washed it, put it in another flask, ran it again, took it out, put it in another flask, ran it again. We did this 5 times with 5 separate batches of glucose. And at the end, it lost 0.3 of a milligram. That was incredible. It's reusable. Now that raises some very interesting questions about how does it work, which Kobayashi had speculated but was completely wrong. I'll tell you about that in a minute. But we realized that it's so reusable, what we could consider doing is operate the manufacturing process in a flow. What that means, so now the way many chemical processes are run and the way Millad is made is in a huge 1,000-liter reactor with lots of water, lots of glucose, and lots of the al reagent, and lots of tin in a big reactor that's stirred, heated, and then they have to work it up. They have to separate out all the byproduct, which is a mess. They take the aqueous phase and clean it up. But because the indium is hardly consumed and there are no byproducts to separate, what we thought we could do is what is now used even more and more and more in industry is to flow the reactants just through a tube. Rather than having a 1,000-liter reactor, you have a tube, and the tube is packed with the catalyst. So there are pumps that feed the 2 reactants. One is glucose, the other is an allylboron reagent. They feed that in simultaneously through pumps to a reactor that is packed with indium metal powder and some glass beads to make it flow smoothly through the reactor. And then what comes out the end is allosorbitol. So the footprint that you need for this manufacturing is 1/100th of what you need for a massive reactor. And it just runs. So what you do is you change volume for time. You just pump it through continuously. It's a continuous reactor. And this is very, very common in big fine chemical industry. All petroleum cracking is flowed because the volumes are massive. And it goes over a catalyst bed. There's not a lot of that now. It's becoming more and more popular in fine chemicals using catalysts. So the material in the tube should stay there. It just wants to catalyze the reaction between the 2 things that are going in. And then all that comes out is the product. And so you just wait. That's where the productivity is related more to time than it is to volume. So that's where AI came in. What we then did with this idea is contacted our collaborator, who's Professor Klavs Jensen, who's a chemical engineer at MIT, a world-class famous engineer. One of my very best graduate students had just gone to him for 3 years as a postdoc, and now he's an assistant professor at UPenn. But I knew Klavs's work. I knew he was a world expert in flow and flow optimization. So we contacted him and we said, we have this extremely cool process. We would love to make it commercial or have somebody, I'm not going to start a company, but someone already is commercializing it and they want it. So what do you think about collaborating? I sent my postdoc who discovered the process and developed it, Tapas Adak, who was the first author of the paper. I said, I will ship Tapas to MIT because we have no flow expertise here and you're the world's expert. We sent Tapas to MIT. He, together with Federico Florit, was an Italian postdoc with Klavs, collaborated. And Federico used AI-guided optimization called Bayesian optimization to optimize the flow process, which we couldn't do. So they did this optimization using a Bayesian algorithm, but it was a really sophisticated AI process. It was not out-of-the-box AI. He had to do some modifications, and that's why I think the paper really sailed through Nature. So what he had to do is called a multi-objective optimization, which means that we had to optimize both for the yield in one run and the productivity, which is grams per hour. And he had 4 dimensions that were the inputs. That was the flow rate of the 2 reactants going into the tube, the amount of the allyl boron reagent that reacts with the glucose, the temperature, and the amount of ethanol. Now, we need ethanol because the allyl boron reagent that adds the 3 carbon piece is not soluble in water. Glucose is only soluble in water. So we need to find the magic mix of water and ethanol to get both of them soluble enough so that they will react on the indium surface and then form the new bond, and allyl-sorbitol comes out the other end. And that took about 4.5 to 5 months, in which Federico was designing the parameters using the Bayesian optimizer, telling Tapas, okay, let's make these changes, try this flow rate, try this temperature, try this stoichiometry, and then they would measure the yield and the productivity. Now, Klaus is an expert in what's called closed-loop flow optimization, where there's an analytical instrument that reads out the result and then tells a computer what to change autonomously. We couldn't do that with this because this was not something that they had experience optimizing. So there was a human intervention in the loop, but that's why it took longer. But nevertheless, they actually succeeded in finding, using the Bayesian optimizer and what's called a Pareto front, the maximum yield and the maximum productivity given the size of the tube and the amount of indium. So the maximum yield is 100%. We were able to find conditions where all of the glucose was consumed. But to do that, we had to have a fairly slow flow rate because the kinetics of the reaction were such that if it went through too fast, it didn't have time to react. So we had a slow flow rate, we raised the temperature, and we raised the amount of the allylating agent so that we could accelerate the kinetics by temperature and concentration of one of the reactants so that all the glucose was consumed. And we got 100%. Now, the other optimization was for productivity, which is what the manufacturer cares about. How many grams can you make per hour? Now, to do that, you have to slow down you have to speed up the flow so that you can get more out. We lowered the amount of the allyl boron reagent, and we add a little more ethanol to solubilize it. But by increasing the flow rate, what that meant was the effluent still had some glucose in it. But the manufacturer couldn't care less because that is the cheapest by far. It's the allyl boron piece that's the cost driver. So they really care about productivity with respect to the allyl boron reagent. So we lowered the stoichiometry, we sped up the flow, and we added more ethanol to solubilize it so it would react faster. And that's what we found. And we have those 2 parameters that now chemical engineers at Millikan will have to figure out how to scale. Because we were just making hundreds of milligrams. They want to make 30,000 metric tons. But that's what Klaus was so clear about in his section of the manuscript. He's an engineer. And so he did a back-of-the-envelope calculation and said, okay, this is how much indium you're going to need because only a tiny amount is actually consumed. This is how many months it's going to last. And this is the size of the reactor that you would need in order to produce your 30,000 metric tons. And we put that in the paper. Of course, the chemical engineers at Millikan are going to have to do a really careful cost analysis and realities, but we gave them the guidelines, and then it's up to them to figure out how to put it in practice.
Yes. Well, I'm sure they're very appreciative of such an efficient process. this brings me to my last question because we did cover how AI advanced your research pretty well there. I'd just like to check if there's anything you'd like to add that we haven't covered yet.
Well, I know this is an open for a lot of different audiences.
Yes.
And so what I feel is the most exciting and interesting part beyond and Millad 8000 is sort of inside baseball, and that would be for chemists only. But I think if I've piqued the interest of a general audience, the things that I'm most excited about now going forward, since we're not manufacturers, is what else can we do with this kind of chemistry? Number one. And number two, how the heck does it work? How the heck does ppm levels of indium catalyze the reaction between these two things with complete efficiency, no side products, and very high stereoselectivity? We make a new stereo center about 8-to-1 selectivity. So the things we haven't touched on is we've figured it out. So the third author on this paper is named Matthew allylboronic. He is one of my current graduate students, and I asked him, and he was excited about the opportunity to drill down and figure out, how does this work? Now, Kobayashi in 2008 made a proposal that it was a surface phenomenon. And he did some surface analysis that was misleading because the technique that he used was going too deep into the indium layer. And the surface analysis was wrong. It missed it. We had a hint in that we found the solutions after the reaction had about 100 to 120 parts per million of soluble indium. And we proved that those solutions were still catalytically active. So we could take the indium metal out, and we could put in more glucose and allyl reagent, and it still reacted. So that told us that there was some leaching of the surface, something on the surface of the indium getting into solution, and that was the catalyst. So Matthew has done a masterful job at proving that and showing with very careful control experiments what combination of the starting materials and importantly also the product are essential for extracting indium hydroxide that is normally on the surface of the indium metal. Indium metal in air gets passivated. What that means is it reacts with water to make a hydroxide layer. It's a very thin coating, micrometers thick. And Kobayashi missed that. And we have shown that under the reaction conditions, that very thin layer of hydroxide gets solubilized. And we've proved it by ICP mass spec analysis. We've proved it by XPS, which is a very sensitive surface analysis technique that only goes down just a few angstroms into the layer, and we could see it. You can tell the difference between indium metal and indium oxides by this technique. So we were able to show it's the oxide that's getting solubilized, and that's the catalyst. So that's one thing that's really cool that we figured it out. And secondly, our future is that we want to add more complicated building blocks onto sugars to do de novo synthesis of non-natural carbohydrates without protecting groups. So when one does try to build up carbohydrates from smaller building blocks, these are polyols, you have to protect them to do organic chemistry. But what we're able to do is take a 4-carbon sugar building block and add a 3 or 4 carbon unit in water, no protecting groups. So we want to make more sophisticated blocks to attach to the allylating agent that contain nitrogen, that contain oxygen, that contain more carbons, and add them into the sugar to make a more complex carbohydrate de novo. So this technology is going to branch us off to a new direction in sugar chemistry, which my group has never done before. So this is an exciting dimension for us.
That's wonderful. Well, we'll have to follow up with you to hear about your next project then.
Okay, great. Thank you.
Thank you so much.